So we're going to start our next module over triangles. And to begin that module, I want to start off talking about right triangles. And those are triangles that have a right angle in them. And we're going to explore different aspects of a right triangle, different facts that might help us to better use them. Now, the first thing I want to look at is this thing, the Pythagorean theorem. And I want to give you the Pythagorean theorem, show you how to use it, but also I want to show you a proof of it. Now, before we do this proof, I want to say just a bit of something that you already know, and that is, how do we compute area? For example, if we want to compute the area of a rectangle, like this rectangle right here. Now, I know you know how to do this already. Somewhere back in your elementary school days, you were shown how to compute the area of a rectangle. But you'll notice what you have is you have the width and you have the length. And notice that there are 3 of these little squares stacked up here that correspond to this 3. So there's 1, 2, 3, and then how many stacks of 3 are there? Well, there's 1, 2, 3, 4, as indicated here. So each one of these little 1 by 1 units have an area of 1. So the area of this stack right here is 1, 2, 3. So you got 3, 6, 9, 12. So what you would do to compute the area is simply take the length times width. So what we have here is 3 times 4, which is 12. 12 square units. Now, it turns out a triangle, now I haven't really defined a triangle, but you know what a triangle is. You've got 3 sides and 3 angles, these closed figures like this. If you notice, a triangle is half of a rectangle. For example, this triangle right here is half of this rectangle. And in fact, if you just half it by sending a diagonal down here, you get half of that rectangle. So instead of it being length times width, it's 1/2 of that. So what we would say is 1/2 of the length times width. So you get this, which is 1/2 of 12, which is 6. Now, usually when we talk about triangles, we don't say 1/2 of length times width. We say 1/2 of base times height. And the way we talk about the height is we have one side of the triangle right here, and then from there we make a perpendicular that goes up. So in other words, the height, base times height, this is the base, and then here's a perpendicular that goes up from there. So it's from the base to the top of the triangle. Now we could turn the triangle around the other way and look upon this is the base and this is the height. But the point is it's 1/2 base times the height. Now this was the area. What we did here was we found the area of a right triangle. Doesn't have to be a right triangle. Notice this triangle here. Okay. If we want to find the area of this triangle, it's still 1/2 base times height. Now, you can see that it's half of a rectangle by looking at this picture I've drawn. You know, I've got this. This in black is the triangle. And I could go ahead and complete this, make a couple of little rectangles or triangles out here. And notice the area of each one of these triangles is 2 times 3, 1/2 of that. 1/2 base times height. So 1/2, 2 times 3, which is 3, and there are 2 of them. 3, 6. So the area of the red triangles is 6. And now, if you look at the area of this triangle, you've got 1/2 base. Let's just look at this. 1, 2, 3, 4 times height, the perpendicular here, 1, 2, 3. See? So 1/2, 2 times 1/2, 4, 1, 2, 3, 4 times 3, and that again is 6. Now, when you're finding area of a triangle, and that's not the focus of this video, but just while we're talking about area of triangles, sometimes the height gives us a little trouble just identifying the height. For example, if you look at this triangle here, this is a weird looking triangle. You've got a base down here, and then you've got a height. Well, this height is perpendicular to the base, although it's not part of the base down here, but you would still calculate the area this way. You'd take 1/2 the base, which is 2, times the height, which is 1, 2, 3. So 1/2 base times height, which would give you 3. And if you wanted to, you could explore that a little more, making a rectangle and showing that this is half of some rectangle there. It's not always straightforward to see that, but we don't want to get bogged down in that. I want to get right to proving the Pythagorean theorem. Now, remember, the Pythagorean theorem deals with right triangles. So, for example, we have a right triangle here, and we want to show that this is true, that if you take the length of, if you take one of the lengths, square it, of a leg of the triangle, and add it to another length of a leg of a triangle. Now, this is the non-hypotenuse leg. So, with a triangle, what we have is, we have this side here and this side here. Now, those form the right triangle, the right angle. Okay? And then we have this over here, which is the opposite. It's the side right across from the right angle. And we call that the hypotenuse. And what Pythagorean theorem tells us is that if we take the two sides that are not the hypotenuse and we square it, take the sum of the squares. So I take a squared plus b squared. Pythagorean theorem tells us that that equals the hypotenuse squared. So the sum of the squares of the sides that are not the hypotenuse, okay, that equals the square of the hypotenuse. Now, what I want to do is show you a little proof that will illustrate that. So let's suppose I take this triangle right here, and I just duplicate it. And now this is a random right triangle. You could make it any dimensions you want. But what I've done is I've taken this triangle and I've flipped it. I've moved it around a little bit, and I've got 4 of them. Okay, so here looks like I turned it upside down. Here I flipped it over, flipped it, rearranged them. And I get these things. Okay, I get these 4 triangles. Now, what I can do with these is I can move them, I can move them together. So in other words, I can take this triangle here and move it down like that. I can take this triangle over here and move it over here like this. And I can take this triangle here, Let me see if I can catch this one without messing with the other one. I can move it like that. So in other words, I can move those triangles together, and I get something like this right here. Now, what I would like to do is calculate the area of this little square thing that I've got here. Okay? I'd like to calculate the area. The area inside. Now, one way you could do it is you could say, okay, I know that the area of this square inside is c squared. I know that for sure because I know that it's length times width, or a square, c times c squared. So I've got the area, which is equal to c squared plus 4 of these triangles. Look at this. I've got this triangle, this triangle, this triangle, and this triangle. So I've got 4 of these bad boys. 4 times 1/2 base, we'll call it b, times height. See? Here's my base, and here's my height. I've got 4 of those. So the area looks like this. The area is c squared plus 2ab. There's what it is. That's the area. That takes into consideration the square and then these four triangles. That is all of the area. Now, if you look at if I look at it a little differently, if I say, well, I'm just going to do it with one move here. I've got a square that side is a times b. So this is an a times b square. Or it's an a plus b, I'm sorry. It's an a plus b length and a plus b width. So if I want to get the area, I could, instead of doing all this, adding the various parts, I could just say, well, it's a plus b times a plus b squared, which is a plus b times a plus b. Now, some people might say, well, that's just a squared plus b squared. But no, don't fall into that trap. What you've got to do is you've got to distribute. So a times a, that's a squared plus ab, plus, now distribute the b through, plus another ab, plus b squared. So it looks like that's going to be a squared plus 2ab plus b squared. Now that's the area of that shape too. So now the areas are the same, no matter how I calculate it. So what I've got, on the one hand, I've got the area c squared plus 2ab, and on the other hand, I've got a squared plus 2ab plus b squared. Now you notice the 2ab here and here, those are both positive 2ab. So what I've got, those will just get rid of each other. I take both of those away, and what I get is c squared equals a squared plus b squared. Now that is the Pythagorean theorem. And now you know a proof of the Pythagorean theorem. You don't have to just take it, take your teacher's word for it. You know a proof of Pythagorean theorem. So there it is. So now we're going to take it as a given that c squared equals a squared plus b squared. Now we go down here and let's see how this works. So I've got a triangle right here. Let's just look at this triangle. And I want to figure out what the hypotenuse is. Okay, so here it goes. I've got the hypotenuse. Now this is uppercase C right here. This is supposed to be an uppercase C. And this is lowercase c over here. That's usually the way we would write that. So here's what we've got. We've got 3 squared plus 4 squared equals c squared. See? A squared plus b squared equals c squared. Now, that will give us 9 plus 16 equals c squared. Okay? That gives us 25 equals c squared. And that gives us c equals 5 because we take the square root on both sides. Now, really, if you have c squared equals something, you would say c equals plus or minus the square root of that something. But we're dealing with length here, so we're not going to say plus or minus. We're just going to use this positive root. So c squared equals 25 means c equals plus or minus, well, c equals 5. Okay, start to say plus or minus. Okay. Okay, now let's do the same thing over here. Here we've got 6 and 8, and we want to find c. So here we go. We've got c squared equals 6 squared plus 8 squared. That means, let's see what we got here. C squared equals 36 plus 64. That means that c squared equals, what is that, 100? Yeah. So that means that c equals 10. I took the square root. So c equals 10. Now, dig this. Let's just take a minute and dig something that happened here. On this original triangle, I had a side of 3. On this one, I have a side of 6. Here I had a side of 4. Now I have a side of 8. It looks like I multiplied 3 times 2 and got 6, 4 times 2 and got 8. And finally, This side here was 5, and now it's 10. It looks like I multiplied 3 times 2 and got 6, 4 times 2 and got 8, and 5 times 2 and got 10. And that's indeed what I did. We call this a 3, 4, 5 right triangle. See, when one side is 3, another side is 4, and the hypotenuse is 5. That's a 3, 4, 5 right triangle. So if you've got something like this, now you look at this problem down here, you've got A equals 9 and C equals 15. Oh, that looks like part of a 3, 4, 5 because 3 times 3 is 9 and 3 times 5 is 15. So what about the B? Well, 3 times 4 is 12. See, it looks like we just multiplied everything by 3. 3 times 3 is 9. 4 times 3 is 12. And 5 times 3 is 15. Yeah, that's what we did. Now, let me tell you something about this. These little Pythagorean triples. I had to lift off the E there. When you're taking the ACT, they put these on there. In other words, you've got like 60 math questions and you've got an hour. So there's not a lot of time to do a lot of computations. But if you have a Pythagorean theorem, if you have a right triangle measurement problem like this, being aware of these Pythagorean triples, in particular the 3, 4, 5 one, is very helpful. And there are some other Pythagorean triples that are nice that sometimes you'll see on there. I think there's I don't keep them in my memory, but I think there's like a 5, let's see, I think there's like a 5, 12, 13, 8, 15, 17, those things, but you can look those up. Okay, now let's continue on here. So now we have, we want to find A, and we look at, now I notice that I have, I think I accidentally erased some of these things. So we've got B is equal to 20, C is equal to 25. Now it looks like I took the 4 and multiplied it by 5 and the 5 and multiplied it by 5. So I would say that A would be 15. Now you don't have to do it this way. You could say, well, I know that A squared plus B squared equals C squared. And then you can put in, I've got 20 squared equals 25 squared. And then I have A squared here. And then you can just solve. A squared equals 25 squared minus 20 squared. And then you could work it out that way as well. You don't have to recognize the triple. It's just a little shortcut. Okay? So the main thing we just need to know when we're studying right triangles, and I'm trying to bring out the important aspects of a right triangle, is this Pythagorean theorem. Okay? Now, let's look at another Pythagorean triple that I put on here. I forgot that I put this one on here. But I've got 5, 12, 13. Now, you can do this the long way, but you'll notice that I'm multiplying 12 by something and getting 36, 13 by something and getting 39. It looks like I'm multiplying by 3. So I need to multiply 5 by 3 and get 15. There we go. Okay. So you can practice some of these. Now, these down here, 4, 2, I've got A equals 4, B equals 2, C equals whatever. On these ones, you'd probably need to just calculate those out. Those don't look like any triple that we're familiar with. So this is going to be 4 squared. So you got 4 squared plus 2 squared. And that gives you C squared equals 16 plus 4. C squared equals 20. So C equals the square root of 20. Yeah, like that. And, that radical can be simplified. But I often prefer to just leave it like that, because, for example, I could write this as, 4 square roots of like that. I could write 20 as 4 times 5, and then I would get 2 square roots of 5. But the question is, well, what is that equal to? It's kind of hard to estimate what that is, but if you leave it as the square root of 20, you could say, well, that's less than the square root of 25, and that's greater than the square root of 16. Square roots that are very close. So you'd say 4, you'd say the square root of 20 is somewhere between 4 and 5. So that's one of the ways that you can calculate it a little more easily. But this is the square root, or one of the ways that you could estimate, a little more easily than trying to figure out what 2 square roots of 5 is. Now down here we've got a, so I've got a squared plus b squared equals c squared. So that gives you a squared equals 49 minus 9. See, just bring over the 9. And that gives you a squared equals 40, or a equals the square root of 40. And you know that that's somewhere between 6 and 7. Because the square root of 36 is 6 and the square root of 49 is 7. So somewhere in that range there. Okay, now I want to talk about one of the main uses for the Pythagorean theorem, and that is the distance formula. So look, if I've got a couple of points, I've got a point here and a point here, and I want to figure out how far are those apart? What is the distance? Well, notice what you could do. You could say, well, let me just make a triangle out of these bad boys. See? I'll just make a right triangle out of them. And here, I've got one side, another side, and I've got a hypotenuse there. So if I want to figure out, well, what is this side here? What is that side? Well, what I would do is I would say, well, I'm going to subtract the x's. So this is 4 minus 1. And what about the height here? Well, this is 6 minus 2. See, I took the difference of the x's. And sure enough, this is 1, 2, 3. And the difference of the y's, 1, 2, 3, 4. So what we've got here is we've got a triangle, and we've got 3 squared, or just 3 actually. 3, and this is 4. So if we want to know the distance is the square root of 3 squared plus 4 squared. In other words, square root of 25, which is 5. So this distance here is 5. But the distance formula, it's going to be this. It's going to be d squared equals the difference of the x's plus the difference of the y's. And then you could say, well, the distance then is the square root of 4 minus 1 squared plus 6 minus 2 squared. Yeah, like that. And that's the distance formula. Now, that's a very important thing to know. And it immediately follows from the Pythagorean theorem. You need to know the Pythagorean theorem. And you also need to know the distance formula, which is the Pythagorean theorem. Okay? So in mathematics, we don't try to memorize a lot of stuff. But the Pythagorean theorem is one thing you need to memorize because a lot of things come from it. Okay, so that's the distance formula. Now, I want to point out something else about right triangles. Now, each one of these videos, I try to pack a lot of stuff in here. One of the things that I want to look at is I want to talk about these trigonometric functions, trig functions. Okay, so we're looking at trig functions. And all the trig functions is just us looking at ratios in right triangles. So for example, we have a couple of triangles here. I have a triangle I'm naming ABC. And I've got a triangle over here that I'm naming D, E, F. Okay, so we got two triangles there. And you notice that I've got, on this one triangle, I've got 1, 2, 3, 4, 1, 2, 3. And on this triangle over here, I've got 1, 2, 3, 4, 5, 6, 7, 8. So this side has 4 and this side has 8. This side has 3 and this side has 6. So it looks like what I've done here is I've multiplied that ABC, I've multiplied all the sides by 2. So these triangles are similar. The difference between the big triangle and the little triangle is I've multiplied all the sides by 2. Now, I want to point out something to you. I want to just draw your attention to something. Notice that in both cases, we have an angle here and an angle here, and those angles are the same. All I did was increase the length of the sides. Now, you could do this. You could say, well, let's move this triangle over here. And you can see that, yeah, indeed, those are the same angles. Okay? So I'm going to take the sine of angle A. Now, let me illustrate what I just talked about. The sine, when we talk about the sine, S-I-N-E, we abbreviate that as S-I-N, and then we put whatever angle. So if I want the sine of angle A, I take the length of the opposite side and put it over the hypotenuse. So in this case, what I've got here is 3 over 4. See? I took this side, 1, 2, 3. This side, see? 1, 2, 3. And I put it over 1, 2, 3, 4. Okay? Now, I want to do that same thing for the corresponding angle D. It's a corresponding angle. Okay? So here I go. I'm going to do that. So I take 1, here I go. I got 1, 2, 3, 4. Actually, I messed up. I'm sorry. I'm taking 3 over the hypotenuse. I'm sorry. Sorry about that. I got ahead of myself because I want to talk about tangent here in a minute. I'm sorry. Let me just take a minute and let you recover from my mess up. Opposite over hypotenuse. Okay. Now I want to do the same thing for D here. Opposite, which is, let's see that. 1, 2, 3, 4, 5, 6. Okay. So there's 6 over this length here. Now we've already seen that length right there is going to be 10, right? Because it's a Pythagorean triple. This is a 3, 4, 5, and all I did was multiply the sides by 2. Okay. So here's 8, and here is 6. Okay, so that means the hypotenuse is double, not 5, but 10. Now notice I can simplify this. 6 divided by 2 is 3, and 10 divided by 2 is actually, I did it again. This is 5, and this is 5 as well. I did it again. I erased the wrong answer and rewrote the wrong answer. Dad, burn it. Okay, look. Thank you for your patience. But it's opposite over hypotenuse. Okay? Now, thank you for your patience, sincerely. But look, opposite over hypotenuse. Opposite over hypotenuse. Now, dig this. Those have the same ratios. Okay? The same ratios. Sine angle A is the same as angle A, and angle D are the same angles. Okay? And notice they have the same opposite over hypotenuse. Okay? Now, let's look at cosine. Now, look, I have to tell you, I'm not going to mess up again. So, So you don't have to be patient anymore. Cosine is adjacent over hypotenuse. So for this first triangle, we have A, which is going to be 4 over 5. Okay. So that's the adjacent over hypotenuse. And then cosine D. Now, when I say adjacent, notice there are two sides. There's the opposite side, there's the adjacent side, and then there's the hypotenuse. So I'm either talking about opposite or adjacent, and then there's the hypotenuse that stands, it's different. So I've got adjacent over hypotenuse. Now let's look at the cosine of D. Well, it's going to be the adjacent, which is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so here we go. So this is going to be 8 over 10. Now 2 will go into 8 4 times. 2 will go into 10 5 times. So dig this. These two are the same. Okay, up here, these two are the same. Because you're dealing with the same angle there. Now, let's look at tangent. Now, here is what I was thinking about earlier. I have opposite over hypotenuse. So I take the opposite side, 3. Not opposite over adjacent. Opposite over adjacent. So this is going to be 3 over 4. See? 3 over 4. Tangent of D, going to be the same thing. Well, let me write it out. You're going to have 6 over 8, which is 3 over 4. So notice that we can talk about the sine of A as long as the angle is, as long as A and D are congruent, you're going to get the same ratio. That's the way these trig functions work. So you've got the sine, opposite over hypotenuse. The cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. So you need to lock those into your brain. The trigonometric ratios. Those three. Now there are 3 others that we usually look at in trigonometry when you take that course. But right now, these are the 3 that we're going to focus on. Now, if you look at this, so let's look at this one. We want the sine of A, and we want the cosine of B, and so forth. We want all these trigonometric expressions here. So let's look at something. I need to figure. In order to get the sine, I'm going to need the hypotenuse. So I need to compute that hypotenuse. So I've got c squared equals 2 squared plus 7 squared. That means that c squared equals 4 plus 49. That means that c squared equals 53. That means that c is equal to the square root of 53. Okay, now that we have that, we can go ahead and calculate the sine of A. The sine of A is 2 over the square root of 53. Okay. Now let's look at the cosine of B. Okay. Now B is the adjacent. Okay. We're dealing with B now. The adjacent over hypotenuse. So this is 2 over the square root of 53. Well, that's interesting. The sine of A and the cosine of B are the same. Okay. Now let's look at sine B. Sine B, you're going to take the opposite, which is 7, over the hypotenuse. Now let's look at cosine A. Cosine A, adjacent over hypotenuse. Okay. Now this is pretty interesting, but here's the deal. Notice that angle B and angle A are complementary. Yeah. When you have complementary angles, if A and B are complementary, then sine A is going to be equal to cosine B, and vice versa. That's the way complementary angles work, or these trig functions work. Okay? Now, let's look at tan A. Tan A is opposite over adjacent. And tan B is opposite over adjacent. Yeah, there it goes. Okay, now. Okay, moving right along here. A lot of material here. Now, I want to look and see what happens when I take sine A and square it. So let's just look at that. If I take sine A and square it, and I add that to cosine A and square it, let's see what I get. I get 4 over 53 plus 49 over 53. Those have the same denominators, so I'll get 53 over 53. I can just add those, and I get 1. Now, that's pretty darn interesting. Sine squared A plus cosine squared A equals 1. Now, that's true always, and this is called a Pythagorean identity. So that's another thing, another important point. And we could do the same thing for sine squared B. So if you look at sine B and cosine B, you get 1 as well. So this is called a Pythagorean identity. So this is another important concept. Sine squared A plus cosine squared A equals 1. That's one of the things that you need to remember. Okay? Okay, now let's look at this. Let's suppose that you have a right triangle right here. And what I did was I made a altitude in here. Okay? I just made an altitude. I just went from down here and went up here. I did a perpendicular. That's what I did. I guess it's not an altitude for that triangle. It's just I made a perpendicular down here. It starts down here on this base and just goes up. And notice this is parallel to this side. So in other words, I just really made myself another triangle. This triangle right here is this one right here. Now, whenever you do that, what you get is said to be two similar triangles. Now, so here I've got triangle A, B, C. That's the big one. And I'm saying that it's similar to triangle A, B prime, C prime. Okay. Now, what it means for triangles to be similar, it means that if you look at the ratio of the corresponding sides, you get the same number. So let's look at this. And I've got BC, this side right here is 1, 2, 3, 4. B prime C, let's look at that, 1, 2, 3. Okay, I get 4/3. Now, we're not dealing with trig right now. We're just looking at something interesting about similar triangles. Now, let's look at AC. Okay, so AC is 1, 2, 3, 4, 5, 6, 7, 8. And AC prime, whoops, AC prime, 1, 2, 3, 4, 5, 6. Is it 6? 1, 2, 3, 4, 5. Yeah, 6. Which reduces to 4/3. Now, if you have AB, okay, over AB prime, because these are similar triangles, you know that this is going to be 4 over 3. You could compute this if you wanted to. But here is the big idea. If you have similar triangles, and this is an example of similar triangles. Now remember, I'm trying to get the big concepts and emphasize the big concepts. When you have similar triangles, that means they share a common ratio. If you look at corresponding parts, BC corresponds to B prime, C prime. That means if you divide this by its corresponding side, you get the same thing as if you divide this side by this side. They have a corresponding ratio. Now, if you look at the ratio of the areas, like if I take this big triangle and I look at the area, well, it's 1/2 base. And what's the base? 1, 2, 3, 4, 5, 6, 7, 8. 1/2 base times the height, 1, 2, 3, 4. And then if I take the area of the other triangle, which is 1/2 base, 1, 2, 3, 4, 5, 6, times the height, which is 1, 2, 3. Okay, let's see what I get. I notice that, first of all, the 1/2s divide out. I get 32 over 18. Now let's see here. 2 will go into 32 16 times. 2 will go into 18 9 times. Okay. Now, I guess we stop right there. Now, look at this. 16 ninths. 4/3. The ratio for these two triangles, when we looked at the ratio of one side divided by its corresponding side, we always got 4/3, 4/3. When we looked at the ratio of the areas, the area of one triangle over the area of the other, we get 4 squared divided by 3 squared. 4 squared divided by 3 squared. That ratio of 4/3 is what we have for these similar triangles. The ratio of the area then will be that squared. Okay? So dig this. Let's suppose we have a couple of, let's just see how this works. We have similar triangles here. We have DE divided by LM. Those are the corresponding sides. It's 3/7. So now what we want to do is we want to say, okay, what is EF? EF divided by MP. Corresponding sides again. Well, that's going to be 3/7. What about the ratio of the areas? 9/49. See, we just square them. And that's all there is to it. Okay, now I've kept you on here, I think, long enough. I've kind of summarized things down here, some of the key concepts that you need to remember. And then we've got an assignment down here. And I understand if you're exhausted, we'll have class time that we can work on this.